So dilations. So a dilation, if you like, you can think of it as a stretch or a compression. Basically here, if I want to dilate horizontally, so stretch it horizontally, this time I replace x with x divided by a. So y equals function x divided by a. That is a dilation of factor a. Now, if a is bigger than 1, we should see the curve becoming a shallower curve. The domain might be altered. I mean, it might stay the same, because if the original domain was all real x, it's still going to be all real x. But if it had some asymptotes, things like that, they maybe affected the location. The range should be unchanged though. Whereas a vertical dilation, we replace y with y divided by a. So y over a equals function x, but again we more normally see that as y equals a times function x. This one is stretched vertically by a factor of a, but this time if a is bigger than 1, the curve will become steeper, not shallower. And this time, it's the domain that won't be affected, but the range might change, depending on what the range of the original function was. So on one graph, we're going to draw y equals x, y equals a half x, and y equals 2x. So there's y equals x. Now, you can think of y equals a half x two ways for this one. Because am I saying it's y equals x on 2, which would make it a horizontal dilation, factor of 2, or am I saying it's 2y equals x, which would make it a vertical dilation? Either way, you still get the same shape, because it becomes y equals a half x. Remember I said, if I was thinking of it as a horizontal one, if a is bigger than 1, which for a horizontal one this one is, a would be 2, we should end up with a shallower curve, and our line is shallower. If I think of it as 2y equals x, now the a is equal to a half, so I should be getting a shallower curve. So we get the same thing. So y equals 2x is the other way around. Okay, that's lines. We can do it with any shape. Let's say we had the parabola. It's a bit more obvious with this one. There's y equals x squared. Now, y equals a half x squared. Because the x is squared, I'm going to think of this as 2y is equal to x squared. If I wanted to group it with the x, then the dilation factor horizontally would not be 2. It would be, what? Yeah, square root of 2. Because I could rewrite that as x over the square root of 2 all squared. So then it's grouped with the x. Anyway. So, okay, if I think of it as 2y equals x squared, then the vertical dilation factor is a half. Therefore, we should be getting a shallower curve, because when it was vertical, we said if a is bigger than 1, we get a steeper graph. So in other words, there it is underneath the curve. Y equals 2x squared, then we should see the opposite thing. So we get a steeper parabola. So now we can have a little bit of fun. X squared plus y squared on 4 is equal to 1. So we must have started with our basic circle. But what have we done to it? X squared, we've left it alone. So nothing's happening horizontally. Vertically, something is happening. So if I group it with the y, so I can see it more obviously what's happening there, then I would have y on 2 all squared. So the dilation factor is 2. But that's when it's grouped with the y. So when it was grouped with the y, we said if it was bigger than 1, we get a steeper curve. We should see a steeper one. So we're going to stretch it vertically. So if you imagine that circle there, if I was to stretch it vertically, that will become steeper. And we end up with an ellipse. There it is. And you'll notice the domain did not change. It was the range that was altered, which is what we said. If we're changing the y, dilating the y, the domain should stay the same, but the range changes. Okay, what about enlargements? See, these are all these things you probably did back in year 7, but a lot more informally. Your translation, reflection, rotation, enlargements. If you apply the same dilation factor to both horizontally and vertically, you should simply get an enlargement of the original shape. So it would be similar figures, if you like. So function xy will become function x on a, y on a. We're changing both of them. Okay. So we're going to get a circle. X minus 1 squared plus y plus 2 squared equals 1. And we're going to enlarge it by a factor of 2. Using the origin as the centre of enlargement, find the circle's new equation. So what on earth's going on here? Well, first thing they've told me is it's enlarged by a factor of 2. So my dilation factor is 2. So therefore I'm going to change my equation to x on 2 minus 1 squared plus y on 2 plus 2 squared is equal to 1. Now to make it more obvious what that is, let's just multiply, get rid of the fractions. We'll multiply everything by, well actually it's going to be by 4, isn't it? Because it'll be the 2's inside the square. So we'll end up with x minus 2 squared plus y plus 4 squared equals 4. And we can see quite easily by looking at the equation what in fact we've got. So indeed it is still a circle, and of course all circles are similar, but one is enlarged. It's twice as big. Now when we say twice as big, what's happening with the areas on this one? The original circle and our new circle, what would be the ratio of their areas? Got to be 4. Because your linear measurements, you've multiplied by 2. So your area measurements, which is units squared, must be 2 squared, which is 4. If it was a solid shape, and we said, how did the volumes compare? Then it would have been 8 times as large. Not all transformations commute. So what do I mean by that? What I mean by that is the order that you do the transformations in. So what we say is a mathematical operation will commute if the order of the objects being operated on doesn't matter. Right? So for instance, addition and multiplication, they commute. 3 plus 4 is 4 plus 3. I can swap those numbers around, perform the same operation, get the same answer. Multiplication commutes. Subtraction and division do not commute. 3 minus 4, if I swap the numbers around but do the same operation, I get a different answer. Same with division. So that's what it means when we say an operation in mathematics commutes. We swap the things we're operating on, we get the same answer. Well, transformations can be done in any order. So most transformations will commute. The exception is if you have a dilation and a translation in the same direction. So if they're both horizontal or they're both vertical. Otherwise, it should commute fine. So let's have a look. If we grab this random curve here, to get to position 1, then first of all I would reflect in x equals 0 and then shift it a units to the right. A reflection, by the way, could also be described as a dilation of factor -1. However, I did it in the other order. So to get the second curve, if I shifted right first, so I moved the blue curve over to A, and then reflected in x equals 0, we get a different curve. So in this case, the transformations don't commute. All other transformations do commute. It's just that if they are a combination of a dilation and a translation in the same direction, they will not commute. So let's determine the equation after y equals x squared has been shifted, then reflected. So x squared, if the first thing I'm going to do is shift it up 1, would become x squared plus 1. When I reflect it, it will be then the negative of all of that because I'm reflecting it vertically. So it's grouped with the y if you like. So we get y equals minus x squared minus 1. If I go the other way, if I reflect vertically, then shift up 1 unit. This time, so the x squared will go to minus x squared, and then I'll shift it up, and I get minus x squared plus 1. So we get 2 different curves. So when you have a translation and a reflection in the same direction, they don't commute. The order is important. Otherwise, we should be fine. Okay, so 3h and 3i.